In this video, we're going to discuss series equivalent circuits. Specifically, we'll get into series resistance and the voltage divider rule. So the whole idea behind equivalent circuits is that we have some subcircuit of interest, and there's a more complex circuit that we want to replace by an equivalent circuit. And for these two circuits to be equivalent, we have to make our substitution in such a way that the currents, powers, and voltages in the subcircuit of interest are unaffected. So that's the whole idea. Now, when we're making a substitution like this, we have to be careful of our nodes A and B. We can't lose them somehow. You'll see how that's possible later. But let's consider now series equivalent resistance. So we'll start with a simple circuit of a voltage source and 3 resistors in series. We're going to go ahead and label our nodes. And because everything is in series, we already know from Kirchhoff's current law that there's one and the same current that flows through all the elements here. We'll just call it I. And we could identify voltage drops across each of these resistors. So because the current goes clockwise, we'll start off with a V1. We can specify the polarity of V1 like this because that is consistent with the current I, according to the passive reference convention. So we'll put here a V2, and then a V3, also consistent with the passive reference convention. We know that by Ohm's law, V1 is I R1, and so on, that the sum of voltage drops across the loop is 0. Right? So if we go from D to A, we have negative Vs. Then we have a voltage drop of V1 as we go from A to B, a voltage drop of V2 from B to C, and a voltage drop of V3 going from C back to D. All that has to be 0, so we can rewrite this as follows. Now, if we combine Ohm's law and KVL, we have this. We can factor out the current because it's the same current flowing through all elements in series. And now what you could see is we could replace these 3 series resistances with one equivalent resistance, Req, so that our equivalent circuit looks like this. Notice that before it was nodes A and D that were connected across the voltage source. So that means that this has to be node A and this has to be node D. So that means that nodes B and C are lost or swallowed up inside the equivalent resistance. So that's just a minor detail to be careful about. Sometimes it'll become important. So there's our equivalent circuit. Now we're ready to see voltage divider. If we're interested in the voltage across any of these resistors, R1, R2, R3, well, we know that it's the same current, so I'll put here, for example, V2, IR2, but we know from this circuit, everything's the same. It's an equivalent circuit. Why? Because it's the same I that flows through here. That's because of this equation. It's the same I. It's the same voltage, Vs, from nodes A to B. So from this circuit, we know that I is equal to Vs over Req. That's just Ohm's law. So we can take this Ohm's law expression and plug it back in here. So what this tells us is that the voltage V2 is proportionate to Vs, and that constant of proportionality is R2, the resistor of interest, divided by the total equivalent resistance. So generally, we'll say the following. For a series of resistances, you can just add them up and get an equivalent resistance. Additionally, if you know the voltage across those resistors, you can get the voltage across any one in particular. So one example of this might be a pair of 1 kilo ohm resistors. Well, that's the same as the voltage source and a 2 kilo ohm resistor. And let's say, for example, we know that this voltage source is providing 12 volts, well then it must be that from nodes A to B, it's going to be 12 volts, and that's fine. So the voltage has to divide evenly, right? Because you wouldn't expect it to be any different between these two resistors. They're equivalent, so that it's a 12 volt drop from A to B still. So this being the midpoint, so this is going to be 6 volts and 6 volts. Another example might be a 3 resistor case. Suppose we defined a voltage like this. Well, we already know that there's a current that goes this way, but notice that that current and the voltage do not satisfy the passive reference convention. So in this case, our voltage divider needs to have a negative sign. Okay, so that was a brief introduction to series equivalent resistors.